this video, I'm going to dig into the details of TCP connection setup and teardown. This is a deeper look than sort of the initial service model we presented, looking at a couple of edge cases and the entire TCP state diagram. So we're going to look at three-way handshake, something called simultaneous open, which turns out to be really important today in peer-to-peer applications, and actually show the full TCP state machine for connection setup and teardown. So the high-level problem here is if we want to communicate reliably, it turns out it's very helpful to have state on one or both ends of the connection. You can, in fact, turns out you can communicate reliably with having something stateless on one end or the other, but it's much less efficient. Having a little bit of state is great. It'll make you have much better throughput, etc. But if we have this state, there's this problem of how do we set up that state? What is it? So connection establishment. But then also, given the state's going to take up RAM in your machine, when can you tear it down? Can you sort of garbage collect this state and reuse it? So examples of this, the memory structures you're using for your TCP connection, the buffers, or also the port numbers that you've used. So there are these problems of connection establishment and teardown. So here's the standard TCP header with its standard 20-byte payload and then options. So for connection setup, as we've seen before, there are four parts of the header that are used: the sequence number, the acknowledgement number, the ACK bit, and the SYN bit. So here I'm going to walk through the three-way handshake in a little bit more detail as to what happens in the packets that are exchanged. So recall in the standard three-way handshake model, we have an active opener and a passive opener. The passive opener is sitting, listening, waiting for connection requests, such as, say, a web server. The active opener is the one who initiates the request to start the connection. So in the first step, the active opener sends a TCP segment with the SYN bit set to indicate that it's synchronizing the passive side to the beginning of its stream. It's saying, what is the first sequence number of my stream? And so let's call it S sub A. So you do this rather than just say assume 0 for a bunch of reasons. Number one, it's very helpful to randomize your starting sequence number for security reasons. It means that people can guess where your stream starts and try to insert data on you. Also, it's useful if there happen to be old packets flying around the internet, which sometimes happens. You could have tremendous delay somewhere. If you randomize your starting sequence number, then it becomes very unlikely that some random segment, or perhaps a corrupted segment, is going to overlap your own sequence window. So the active side sends a SYN saying, this is my starting sequence number, S sub A. The passive side responds, also with a SYN, saying, okay, I'm going to synchronize you. My starting sequence number is, let's say, S sub P for passive. But I'm also going to set the ACK bit, which means that the acknowledgement sequence number in the packet is valid. And I'm going to ACK SA plus 1. Recall that a node acknowledges not the last byte received, but rather the first byte that hasn't been received. So by sending ACK SA plus 1, the passive side has acknowledged that it received the SYN, which is effectively byte S sub A. The active side then responds. It doesn't need to send a SYN because it's synchronized. So it sends a packet with sequence number SP plus 1, that's commonly what's used, and ACK it sends a packet with SA plus 1 and ACK SP plus 1. And so now it's acknowledging, saying, I have received your SYN and I'm acknowledging that. Now this initial packet, the sequence number is SA plus 1, but it tends to be of 0 length. So if there were a byte in the packet, it would be SA plus 1, but it's not, and so it's of length 0. This is just a simple control packet. And so there's the sequence number of which the bytes would start, but there are no bytes. So that's the basic connection setup. SYN, SYN-ACK, ACK, A plus 1, P plus 1, and then an empty segment just for connection establishment. So it turns out TCP also supports another way of opening a connection, something that's called simultaneous open, which, as I said, is used a lot, as we'll see later in the course, in peer-to-peer applications to reverse things called network address translation boxes. And so the way simultaneous open works is this happens if the two sides, we call them active and passive, but now they're really both active, both know each other's port numbers. So the node on the left knows that the port that the node on the right is issuing a connection request from. The node on the right knows the same for the node on the left. And so they're using the correct port numbers. And they do this, they negotiate the say beforehand. So what happens with simultaneous open is both sides send SYNs at the same time. And so here the one on the left sends a SYN. Let's call it just S sub A again, S sub A. But at the same time, the node on the right sends a SYN, S sub P. Well, the node on the left responds, and it sends SYN, S sub A, ACK, S sub P plus 1. Similarly, the node on the right responds with SYN, S sub P, ACK, S sub A plus 1. At this point, we've now established the connection. Both sides are synchronized to know the starting sequence numbers. They've acknowledged that. But note that this takes 4 messages rather than 3. So let's see this just a standard three-way handshake in practice. So here I've opened up Wireshark, filtering on port 80 and a certain IP address. And so I'm just going to telnet to port 80 on that host, and we'll see the SYN, ACK, ACK setup. And so there it is. So here's the first packet sent from my host to the destination. And we see that it's an HTTP port 80, SYN sequence number 0, and there's no ACK sent. There's no ACK bit, and so the acknowledgement field is invalid, so it's not displayed. Now, it turns out the sequence number in this packet isn't actually 0. What tools like Wireshark do, just to make things easier to read, is they use relative sequence numbers. So they show you what the sequence number is relative to the beginning of the stream. And since we're just starting the scene, we see sequence number 0. If we dig inside the packet, down here at the bottom, you can see Wireshark tells you sequence number 0, relative sequence number. And if we then look at the actual field, it's CCBD1DBB. And so it's much larger than 0. Now, what we then see is for the second packet that's acknowledging this, it's going to acknowledge with CCBD1DBC. Here, again, it's using relative ACK numbers, but that's what we see, CCBD1DBC. It's also sending a SYN, so here's the SYN ACK. And so the sequence number, again, a relative sequence number of 0, but it's 341135 AE. So this is from my host to the server. This is the server back with the SYN ACK. Then my host responds with an ACK. And so you can see sequence number 1, acknowledgement number 1. So it's acknowledging the SYN that was sent from the server. And it gives us sequence number 1, but it's a length of 0. And so it's saying, aha, this packet contains the stream starting at byte 1, but there's nothing in it, so there's actually no data yet. So there we see a simple three-way handshake. So now let's look at a TCP connection when there is data. So we're going to see the SYN, ACK, and then some data communication. So I can do the same thing as before, except this time, rather than telnetting to port 80 where there's no data transferred, I'm just going to do a standard web request to port 80. And so here we see a TCP connection. And so here we have the SYN, ACK, ACK. So now the connection's been established, and then data transmission starts. And so here's a packet showing it's HTTP. And if we look inside this particular TCP segment, see sequence number 1. So it's the start of the data stream. Length 474. So this particular chunk of data was 474 bytes long. So the next sequence number would be 475, still ACK1. And so there's the data that we're sending as this request to the web server. Then the web server responds, and responds with ACK 475. Right? So the next byte to expect is 475, but sequence number 1. So this is just length 0. This ACK, it has no data in it. This is what we call sort of just an ACK packet, right? And so it has no TCP segment data, but is acknowledging the data that it's received. The next packet, though, from the server actually has data in it. So we can see here length 1448, but sequence number 1. So it's 1 to 1449. And here's the next TCP segment. And then we see here, putting that together, there's the HTTP response, which it's put together. And so there we see the connection establishment, and now the sequence and acknowledgement number spaces are walking forward according to the data communication. So next, we're going to look at how TCP tears down a connection. Like connection setup, this uses the sequence number and acknowledgement number fields. But unlike connection setup, which uses the synchronization bit to synchronize sequence numbers, connection teardown uses the fin bit to denote that there's no more data to send. So it uses the ACK and fin bits. And so when TCP sends a packet with the fin bit, what this means is that that sender has no more data to send. This is the end of the stream. This is caused when you say call close or shut down in the application. But TCP connections, like most reliable connections, are bidirectional. And so it's not until both sides have nothing to send that you actually terminate the connection. Because it could be one side is done, but the other side has more to send. And so it's not until both sides have finned and you've acknowledged those that you can tear things down. So a typical teardown exchange looks like this, where we say have A and B who are communicating, and A closes first. And so it sends a packet with the fin bit with sequence number S sub A and acknowledging S sub B. B then sends a packet to acknowledge this fin, so ACKs S sub A plus 1. Then at some point later, B decides it needs to close its side of the connection, so it sends a fin, sequence number S sub B, acknowledgement S sub 1, it's still acknowledging SA plus 1, which then A responds saying, I'll acknowledge SB plus 1. So fin, like SYN, represents of the last byte of the connection. The way that you, like SYN represents the first byte, the way you acknowledge is by acknowledging plus 1. With fin, you acknowledge that you received it by acknowledging plus 1. Of course, you can also have simultaneous close where they send the fins in parallel and the same exchange occurs. Great, so now we've exchanged these messages and we've acknowledged them. When can we actually tear down the connection? When can we actually delete the state? When can we reuse the ports? This turns out to be non-trivial. You can't do it immediately. So, for example, what happens if this final ACK is lost in the network? So I've sent fin, then I receive a fin, and I ACK it. I can't immediately tear down my connection. Because what happens if that ACK is lost? The other side's never going to hear it. It's never going to know whether the connection was torn down. Another issue is it could be that we do a fin ACK, and acknowledge and tear down, and then the same port pair is used immediately for a new connection. We want to make sure that we don't, by accident, then corrupt the data because the sequence number spaces overlap. So the solution that's used is the active closer goes into something called time wait. And what this means is that if I'm the person who sends the fin first, then once the connection is torn down, I have to wait a little while before I can reuse my state. And so you keep the socket around for two what's sort of maximum segment lifetimes, or 2 times or what you'd expect to be the longest time segments might live in the network, which is on the order of, say, a minute or so. So this approach of 2 maximum segment lifetimes can pose problems with servers. In particular, if I have a server and it says tons and tons of sockets which are in this time wait state, this can slow things down if the server was the one closing first. So there are tricks. You can send a reset to delete the socket. You can set an option to make the linger time to be 0. Another issue is the OS might not let you reuse a port because it's still in use. There is an option you can do called SO reuse adder that'll let you to rebind a port number. So this is useful if, say, you're just debugging something and, gosh, I don't want to wait 2 hours just because I happen to have finned in this order. So let's see what a connection teardown looks like. So here's a basic connection setup, SYN, ACK, and then here's the teardown. So because we are exchanging data, we have the acknowledgement bit set. So here's the fin. Here's the initial fin from my host when I close the connection. And so it sets the fin bit, ACK1, sequence number 1, ACK1. Then the server, in response, is also closing. So it sends a fin, sequence number 1, ACK2. So it's acknowledging my fin. And then my host responds with an ACK for that fin, sequence number 2, ACK2. So here's a simple 3-way handshake for tearing down the connection. Fin, acknowledging some prior data, acknowledging the fin, sending your own fin, and then acknowledging the fin. So now if we put all of this together, we can see what the full TCP finite state machine looks like. And so this is something you're going to come across many, many times. This is well-established finite state machine that really sort of lays the groundwork for how you want to set up reliable connections. And so I'm going to walk through it. It looks pretty complicated when you first see it, but it's because there are a couple of cases. And actually, given what we've presented before, it should all be pretty simple. So first, we're starting in the closed state. So this is when there are no connections open. I'm just sitting there. My application has not tried to open a connection. So then the first transition here to the listen state, This is the passive openers. This is a server. A server is listening for connections. So you can see the action is listen, and there's no packets exchanged. If you close it, you then return to the closed state. So this, if I'm listening for connections, I hear nothing, or return to the closed state. The other transition out of the closed state is the active open. So here's the connect. And connect causes a SYN packet to be sent. So this is step one of the three-way handshake. So you send a SYN, and you're now in the SYN send state, SYN sent state. So this is the active side. These red lines are showing the active opener of the three-way connection. So SYN sent. Then if you receive a SYN and ACK, so this is the stage 2, you send an ACK, and now the connection is established. So this path here, this is the active opener. Now let's watch the passive opener. So the passive opener is in the listen state, and it receives a SYN from an active opener. In response, it sends a SYN ACK and enters the SYN receive state. Then if it receives an acknowledgement for its SYN, this is stage 3 of the three-way handshake. It's the reflection of this step here. Then the connection has been established. Now, if you're in the listen state, it's possible that you can also call send, which will then result in sending a SYN message. Or you can also, in that way, you're then going to, even though you're in the listen state, you can actively open and active in an open state. So now there's one more path here, which I mentioned, the four-way simultaneous open, which is this. And so this is when both sides have sent SYN. So we're just looking at one side of the connection. And in response to a SYN, you get a SYN from the other side. And so this is the two SYNs crossing. So in response, you send SYN plus ACK, SYN received, then you ACK. And so there's the 4 messages. Each has sent a SYN, each has received a SYN, and then received a SYN, they send a SYN ACK, and then there's an ACK and data exchange can occur. And so now we're in the established state. Now, of course, you can always transition out with respect to closes and resets. But so now at this point, we've gone through connection establishment. Now we're going to go into connection teardown. And so there are 2 cases here. One is that if we're the active closer, here we call close. That results in a FIN message being sent, a FIN packet with a FIN bit. We now enter FIN wait 1. The other is if we receive a FIN, then we acknowledge it. And we're now in the passive close state where the other side is closed. And then when we actually call close, we'll send FIN, send the last ACK, and be closed. And so here close wait is we are still allowed to send data, right, until we call close. So this is the other side is closed, but we haven't. So now when close is called, we're in the FIN 1 state. And there are a bunch of transitions out of that. One is that we receive a FIN. So we've sent a FIN, received a FIN. So this is the example I showed with the TCP teardown. So we've sent a FIN, we receive a FIN, we acknowledge it, we're now in the closing state. We then transition to time wait. Another is that we receive a FIN plus an ACK. So we can just acknowledge that and enter time wait. The final one is that we receive an ACK, but no FIN. So this is, we have closed our side of the connection, the other side hasn't. And so it's sort of this state here is correlated with this state here. Then when we do receive the FIN, we acknowledge it and enter the time wait state. And then we have the time up before we can actually close and recover the state. So you can ask, what's the difference between this transition to closing and time wait? The reason is that this transition to closing is when the 2 FINs pass each other. So I send a FIN, the other side sends me a FIN, but hasn't acknowledged my FIN. This is the difference between FIN/ACK and FIN plus ACK/ACK. And so then I wait for that FIN to be acknowledged and then transition to time wait. So this is the full TCP finite state machine. It looks really complicated. I mean, it does have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 states. But when you realize it breaks into these 2 parts, connection establishment, connection teardown, and really there's just a bunch of different possible ways the FINs can be exchanged, it's actually not that complicated. And so I encourage you to open up Wireshark and just open up a couple of web connections, just see what's happening with your TCP connections. And you'll be able to see how those different connections are traversing this finite state machine.